Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, we're going to talk about the design of nailed connections for wood. So in previous videos, we've looked at what nails look like. We've looked at a bunch of example nailed connections. We've looked at some tips for how to design good connections. And in this video, we're going to get into the nitty-gritty of how do we actually calculate the strength of nailed connections and what are the mechanics behind nailed connections and how they resist loads, specifically lateral loads, which means shear loads between two members, which means I could have two wood members like this, and I will put a nail through to connect the two of them, and that nail will prevent loads like in this direction or in this direction. That's what we mean by lateral connected nailed members. So nails are really popular way to put together wood, and that's because light frame timber construction is one of the most popular types of construction, probably by far the most popular type of construction for residential housing. And so there's a lot of nailed fasteners used every year. They're really easy to install. Hammer and nail is kind of the simplest way, but in housing construction, it's much faster to use pneumatic nailers. And the other nice thing about nailed connections is that they're very ductile. So when nails bend, the steel yields, and that yielding process is a ductile process, and that means that in earthquake, for example, we can get quite a lot of energy dissipation out of nailed connections, which means that we can have, pretty high earthquake performance actually from those types of connections. Okay, so let's take a look at the kind of anatomy of a common nail. Okay, so this is what a nail looks like. Probably most of us have seen nails before. It has a head. The head keeps the nail from being driven in too far and provides a resistance to help with withdrawal. It's got a long circular shank, so the cross section is round, and then it has a point which helps with driving the nail in the first place. And regular common nails come in lengths about 1 inch to 6 inches, and then on top of that we have a couple other types like spikes, which basically have the same geometry but are just wider and longer. And then there's also common spiral nails. Which have a shank that has kind of a spiral pattern in it. And but they all basically have the same kind of strengths, and it's going to depend on the cross-sectional size of the nail. Now you can find these nail properties in a table in the back of the standard in the appendix. That table looks something like this. It has a different number if you're talking about the 08614 versus 19 standard. But basically it has all of these different common wire nail lengths. And you can see that there's not infinite possibilities of combinations of length and diameter. So basically for a given length, generally that already defines your diameter. So I can't get like a 2-inch nail with a 1.83 millimeter diameter. It's not possible. Now, yeah, it is the case as well that in this table we have kind of mixed units here. We have length in inches, but diameter in millimeters. All the inputs that we use in our equations are going to be in millimeters. So I do need to convert these lengths to millimeters when I'm trying to calculate, embedment length and stuff like that. But they're given in inches because this is the dimension that the nails are commonly available in. Because they're just commonly available in imperial sizes because most of them are presumably sourced from the United States. And that's why these diameter numbers are also not kind of whole numbers. So there's only a few cases here where I have, basically, no, there are no cases. Every single case has a different length, has a different size. So I can specify basically based on the length of nail and the gauge. Gauge is just another measure for size, but gauge goes in the opposite direction of diameter. So a larger gauge number means a smaller diameter. Smaller gauge number means a larger diameter. Okay, and this goes on. So those are the wire nails. Then also we have the spikes, which as I mentioned are just like nails except bigger. And you can see they have a very large diameter. And then there's the spiral nails, which are like the regular nails. They just have a spiral pattern in the shaft. Okay. So the tables are provided there so that you know where to find them in the future. Okay, so let's look at a nailed connection, what it looks like, and how do I define all of the geometry of my nailed connection. So first, the one parameter that we see all the time, and this is for all of the different types of, or for many of the different types of connections, including when we talk about bolts later, is the diameter of the nail. And we're talking here about the cross-sectional diameter. So if I'm talking about a bolt, there we go, I had to find my bolt again. So the diameter of the bolt is the diameter of the cross-section. Okay, so if I'm looking at the cross-section of the bolt, and it would be the same as the nail. You know, for the bolt, it's going to be the diameter of the smooth part of this cross-section, not the threads, because we're going to design our connections so that the shaft is intercepted, just like in steel design, we do the same thing. Okay, so DF is just the diameter, and of course that is a proxy for the area, but in a lot of cases it's the diameter that we need, because most of the cases that we're talking about, you know, if you imagine that this is a nail, is a sideways embedment. So this is a piece of a nail going through a piece of wood sideways. So if I'm pressing, if this is in a hole and I'm pressing on the surface and pushing it through, then it's the diameter. It's the diameter of that shaft that is basically the area that is related to the area of the amount of wood that I'm pushing on. So that's why the diameter is usually important, especially when we're talking about lateral strength of connections. Okay, so here are three different types of timber connections. On the left, I have two different two-member connections. One where I have a piece of wood nailed to another piece of wood, and the second one where I have a piece of steel nailed to another piece of wood. I'll hatch that to show that it's steel. And then one three-member connection on the right, which is where a nail is going through three different pieces of wood at once. Two on one side of the member connection and one on the other. So basically I'm pulling like this. I have two pieces of wood basically gripping another. So for a three-member connection for nails, it means that the nail goes through all three pieces. If I just have nails from one side and the other, each one going through two pieces only, then that's considered two separate two-member connections instead of a three-member connection. So three-member connection requires that we have two different shear planes. Okay, so we looked at shear planes in a previous video. Okay, so we need to get some basically terminology out of the way here. Okay, so in the two-member connections, we always have a head side member and a point side member. So in the second two-member connection there with the steel plate side is the head side member and the wood piece is the point side member. And then in three-member connections, we have two side members and one in the middle, which is our central member. So this one would still be called our head side member. And this one over here would still be called our point side. Okay, and both of those are side members. It's the only difference being that we have now this central member. So I'm going to basically call I'm going to label all of the side members as 1. So this one is a 1 and this one is a 1. And our point side member for the two-member connection, we're going to call 2. And the central member, we're going to call that 2 as well. And the reason that I'm giving these numbers is because this is how we label basically our thicknesses when we're defining the thicknesses of each of these members. Okay, so let's do that now. Okay, so we have thicknesses and we have minimum thicknesses. Okay, and there's a nice, there's a similar figure to this in the standard that lays out all the minimums for thicknesses. So, I mean, I can't put a nail through a sheet of paper, right? Like a sheet of paper, which is technically like a very, very thin piece of wood. You know, I need a minimum thickness in order for the nail to properly engage. And likewise, when the nail goes into the piece of wood, I need a certain amount of distance for embedment so that the nail is actually properly going to stay in that piece of wood. Because this nail is held in friction. So if I just kind of put in a very small part of the nail into that last point side piece of wood, then as soon as I start to shear, it's just going to come right out. Okay, so I need a minimum kind of, we call that the nail penetration length. Okay, so for a wood headside member and a two-member connection, we call that T1, and T1 has to be greater than or equal to 3 times DF, where DF is the diameter of the fastener. So if I have a 3mm fastener, then my headside member has to be at least 9mm thick. I don't have a thickness requirement for the point side member. What I have is a penetration length requirement. We're still going to call this, we're still going to give this a T name. This is going to be T2 in this case, which is the best Terminator movie. And then we are going to put this minimum requirement, which is 5 times the diameter of the fastener. So it's a bit more. Why? Because we need to prevent pull out of the nail. So the embedment depth is has to be a little bit greater. Okay. And of course, as we mentioned before, this is basically what DF is, diameter of the shank. Okay, let's move on to the one with the steel. So for steel member, I have a requirement here that the piece of steel thickness, which is called T1, has to be greater than or equal to 0.9 millimeters. Okay, so I can't use a piece of steel that's thinner basically than about 1 millimeter. As far as the design of that piece of steel goes, just like in any connection, including in bolted connections that we'll talk about later, the piece of steel still needs to be designed, but the design for that piece of steel is not contained in the wood design standard. It is, you're going to have to use the steel design standard S16 in order to design that piece of steel. So that part is not covered in this course. Okay, and then we have the same penetration length requirement here. So this is T2 for member 2, greater than or equal to 5 times DF. Okay, and then for the 3-member connection, for the head side, my T, I'm not gonna give this a T number yet. This value though has to be greater than 3DF, and the penetration length here, just like before, has to be greater than or equal to 5DF. And the main member, the member in the middle, sorry, the central member, this value T2 has to be greater than or equal to 8DF. So those are the requirements for basically any type of wood. There is an additional requirement for if, or there is a less stringent requirement if I'm talking about OSB or glulam. So for head side, for those two values for head side pieces of wood, for plywood or OSB, then in the new version of the standard, but not the old version of the standard, so this is 086-19 only, they have introduced a less stringent requirement for the head side thickness of 2.5 DF. But if you satisfy 3DF, then you satisfy both. So this is a less stringent requirement. Okay, so I haven't labeled these ones on the right here as T1 yet. And there's a reason for that, because in a 3-member connection, now I have 2 different values for T1. So as you might imagine, you know, in order to prevent having to do 2 different cases, one for a head side member and one for the penetration, you know, if these 2 are different, basically what I do for T1 is I take the minimum. So basically the lesser of these two values. Okay, and by the lesser, I don't mean that I find what that minimum is and I use that. I use the actual value. Okay, so if I have a head side member and it's 25 millimeters and a point side member that has an embedment of 20 millimeters, I'm going to use the 20 millimeters as T1, assuming that both of those values are equal to or greater than these requirements of 3DF and 5DF. Okay, so that was the way that they worded it was a little bit confusing in 08614. The requirement hasn't changed, but they have made it a lot more clear in 08619 what they mean of this lesser, the minimum of these two dimensions. So whatever the actual dimension is for the point side member and whatever the actual dimension is for the head side member, I just use the lesser of those two when I'm calculating what T1 is. So T1 for two-member connection is just the head side member thickness. Okay, so the actual head side member thickness, not the minimum, of course. So, you know, I could have 10 DF as my T1. Whatever that size is, that's what I'm going to use as my T1 in my calculations. And for T2, I'm going to use the actual nail penetration. So however far this nail actually gets into that piece of wood is the value that I'm going to use for T2. And for T1 on the right, for three-member connection, as I mentioned, I'm going to use the lesser of the head side or point side for the side members, basically. And for T2, it's going to be the central member thickness, as shown. Okay, so that's all I need to know about the cross-sectional geometry of two-member and three-member connections. So these are how I calculate all of the lengths, the T's, the thicknesses, and embedment lengths that I'm going to use for my nailed member connection calculations. Now, what about in the other direction? So instead of looking at the cross-section, what if I'm looking at the face and we need to determine what is appropriate nail spacing? Okay, so I'm showing a wood member. I'm just going to show it from the point of view of one member for now. When I join multiple members together, this spacing requirement, I have to think a little bit more about it. So right now I'm just looking at one member and I put some nails through it. It's attached to something else, but we're not considering what that is yet. Okay, so this is best case scenario. Okay, so I have some nails. I'm indicating my nails by just some black circles. And obviously I'm going to need some spacing requirements for these nails. Why? Because if I put two nails immediately side by side, if you have worked with nails in wood before, if I put a nail here and I put a nail immediately beside it, I'm probably going to split the piece of wood. Why? Because when I put the nail in, it spreads apart the fibers. It spreads apart the fibers a bit when I put the nail in, right? So I have to spread apart the fibers in order to fit the nail in. Now, if I put my nail in one place, then, my fibers have to bend up and out of the way. And if I go a certain distance away, then the fibers are going to kind of basically come back to being together. So if I have one nail here and I have one, say, way over here, and the fibers are able to go back together in between, then it's not a problem. But as I bring these nails closer and closer together, these spots where the fibers are pulled apart are going to eventually join together. Let me see if I can get this in the same place to make this obvious. Are going to eventually join together, and then they're going to cause a split. And if I split my piece of wood, obviously I'm going to lose a lot of strength because now I have two pieces of wood where before I had one. And so my connection might be totally broken if I split it all apart along the lines of nails. So I have to spread my nails apart far enough so that I don't get this splitting. So I need to allow the fibers to come back together. And that's how they determine these. So obviously putting nails in this direction, I can put them a bit closer because I'm less likely to cause some kind of splitting. But in the longitudinal direction, like the spacing in the longitudinal direction, I should have to put them probably farther apart. And that is exactly what you find when you look at these spacing requirements. So let's look at one of them to start. Okay, I'm going to look at basically the spacing parallel to grain. So that is this spacing here. Okay, one tricky thing between 08614 and 08619 is that in 08619 they have changed the names for all of these spacing parameters. Definitely for the better, but it's a bit confusing if you're going between the two. I'm going to put both. In general, that shouldn't be much of a problem, except that there are two things called A, and they're different things. So pay attention. I mean, if you go to your standard when you're designing and you look at the value that's there, you know, and then you're only dealing with one set of values, should be easy enough. But I'm putting both to future-proof this a little bit. Okay, so this spacing parallel to grain here is called A in 08614, but in 08619 it's called SP, spacing parallel. I mean, that's a kind of better name than A, which just means nothing. Okay, so to give this a little bit more detail, so this is A in 08614, and it's SP in 08619, and that is the spacing parallel to grain. How do I know the grain direction? I have a piece of wood. The grain direction is the same as the longitudinal direction of the piece of wood. So here we can see the piece that we're dealing with. And so in the longitudinal direction, that's the direction of the grain. So if we're talking about nails, here, 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 that's in the direction parallel to grain. So that's what we're talking about here. So the requirement for spacing parallel to grain is that they need to be either 20 df apart or 16 df apart. And that depends on what kind of material that you're talking about. And this is one of those cases where actually the stronger material is a bit worse. Why? Because it's a bit more stiff. So it's harder for those fibers to bend back together to prevent the split from happening. So 20 df is for Douglas fir. It's for these species, Douglas fir, hem fir, and western cedar. So for the rest of these, I'm just going to call this group A. And 16 df is for SPF and northern species, which is kind of a catch-all for the weakest kind of species. And I'm going to call that B. So for the rest, I'm going to say it's 20 df for A, 16 df for species group B. Okay, so that's parallel to grain. Now, what about in the perpendicular to grain direction? So in the perpendicular to grain direction, that parameter, the spacing is called either C in 08614 or SQ, spacing in the Q direction. And Q is something that we've used for perpendicular to grain previously when we talked about compression perpendicular to grain. Remember, that was a QR resistance. So that's why it's Q. And so I'm going to say up here what these are. Okay, and so that's spacing perpendicular to grain. That's the C and the SQ, and these are the requirements: 10 df for that A group of species and 8 df for that B group of species. Okay, so there's two more that we have. One is edge distance. And that is the edge distance perpendicular to grain. Now you remember that edge has a specific meaning. We talked about this in previous video. The edge is basically, if I had a 2x4, it would be the uncut part. Okay, like the part that is not cut across the end grain. Okay, obviously these are all cut, but it's like the smooth part here. It's the edge of the piece of wood, the side of the piece of wood. This is an edge. This is an edge. This is an edge. Okay, the end, which we're going to talk about in a minute, is the surface that we cut when we size the pieces. Okay, so it's the side that when we cut, we see the end grain. That's the end of the piece of wood. Okay, so here, it doesn't matter the direction of the load. I have a distance that I need to keep away from the edge, and I have a different distance that I need to keep away from the end. Okay, so this first one is the edge distance. Okay, D or E. D in 08614, which doesn't mean anything, and E in 08619, which is edge, stands for edge. The reason that these are better is because they line up better with what are the same spacing requirements that are listed for bolts, which haven't changed, but are, they have S and E instead of A, B, C, D, which are just meaningless letters. So this is better. Okay, so this one has 5 DF for the A species and 4 DF for the B species. Okay, last one, as I mentioned, is our end distance. Okay, so this is the end distance. It says parallel to grain because the distance direction is in the direction parallel to grain. Just like when I said edge distance perpendicular to grain, the direction of this line is perpendicular to grain. The direction of the dimension is perpendicular to grain. So this is end distance, and this is the one that's confusing because it has an A, which is used for spacing parallel to grain in 08614, but is now used for end distance parallel to grain in 08619. A is better because A is also what's used for end distance for bolted connections, which we'll talk about later. So just be careful. But if you're working out of the book, then you shouldn't have any problem. You might get confused if you're working directly from this sheet, so better to work from the book. Okay, and this is the requirement, 15 DF for A and 12 DF for B. As you can imagine, the end distance requirement is more stringent than the edge distance. Why? Because if I put a nail close to the end of my piece of wood, I could easily get splitting like this. Okay, so I have to keep it relatively far away. Okay, so those are all of the requirements for my spacing. If I'm just talking about one piece of wood, we're going to talk about multiple pieces in a minute. But there is one more thing, which is that all of these presuppose a certain moisture content. So as I mentioned before, a stiffer member has a more stringent spacing requirement. Just like here, Doug Fir had a more stringent spacing requirement than the less stiff SPF. Since moisture also affects stiffness, we should be aware that if we have a very stiff member because it's very dry, drier than an assumed regular kind of moisture content above 10%, then we could get splitting in those members, even using these spacing requirements. So if we have very dry conditions, then we should consider increasing our spacing requirements and pre-drilling the holes to prevent splitting. So as I mentioned, those requirements were only for a single member. Now, if we have multiple members of wood put together, so if I have two pieces in there put together like this, that's fine. I can use the same spacing requirements. Why? Because the grains are aligned in the same direction. So if I'm looking at spacing between, like, let's say these two holes here, and these are where I put my nails, then my perpendicular to grain direction is the same in this piece of wood as it is in the piece of wood behind. So both the grain is aligned. So then I'll obviously have to consider an end grain distance here that I don't have to consider in the piece behind because there's no end there. And in the piece of wood behind, I'll have to consider the end on this side where I don't have to consider that on the piece of wood behind because that's not where the end is. Okay, so that's if I have like an overlap connection like this. Okay, so my end distances will be the only thing that is different between these two pieces of wood, depending on how I lay out my nails on that interface. Now, if I twist one of those pieces of wood like this, now the grain directions do not align anymore. So that means that if I put two nails in these two holes that are already here, okay, this hole and this hole, then in this direction here, they are perpendicular to grain. So that's a perpendicular to grain distance that I have to check. But in the other piece of wood behind, that direction is the longitudinal to grain direction, the parallel to grain direction. So that means that for the nails connected to the back piece, because they go through both pieces, in the back piece, they need to be farther apart than they have to be in the front piece. So, I mean, there's no way I can nail into these so that I have a different spacing in the back than I do in the front. The spacing is the same in both, right? Because they go through both pieces. So that means I'm going to have to use the more stringent requirement of the two when I calculate how far apart these nails have to be, which is going to be basically the parallel to grain direction spacing, which is more stringent than the perpendicular grain direction spacing, as we talked about for the reasons that we talked about. Okay, when I have things on an angle, it's a little bit more complicated, but there's a very nice figure in the standard that tells you exactly what to do. So I'm going to take a look basically at the case where we have two members connected perpendicular to each other. Okay, so as I mentioned, the parallel to grain spacing in one of these is going to be the perpendicular to grain spacing in the other one when I have an overlap of two of these members. So I'm going to have to use the worst case for both of these spacings. So both of these spacings are basically going to have to be the parallel to grain spacing, which is the worst of the two. So the perpendicular to grain spacing in one is the parallel in the other. And when I say A/SP, I mean it's A in 08614 and it's called SP in 08619. So I'm just putting both there together. So I'm going to use the parallel to grain spacing for both of those directions. And then what about these, which are the edge spacings in both of these? There's no end spacing here because I'm not anywhere close to the end of a piece of wood. So if I'm way in the middle of a piece of wood and my end is like a meter off that way, then I don't really have to worry about my end distance. So here I'm worried about my edge distance. So if I did have an end here, then I would have to use the worst case. And so for example, if one of these members ended, and there's an example like that in the standard that you can look at on your own. So here I'm using edge distance for both, mostly because there is no end. So there's the figure, so that you can go see the other examples. And for diagonally connected members, it's much the same. It's just, are they considered more parallel? You know, if I have two of these that are at a very shallow angle, then, you know, maybe I'll consider them more as being in the same direction, parallel to each other. And if I have a greater angle, then I'm going to consider more that they're more like this case, where they're totally perpendicular. So there's no kind of in-between spacing requirement. It's either I use these or I consider them like this. And it depends on how steep the angle is between the two. Okay, there's one more important thing that we need to talk about, which is the issue of extra nails. And so there's a nice thing here, which is that if I have a matrix setup of nails like this, where I have them all in rows and columns, then I am actually permitted under these spacing requirements to include extra nails at the diagonal intersections between these. So I can put an extra nail here and I can put an extra nail here. So I'm permitted to include extra nails at diagonal intersections between rows. So that includes if the rows are kind of offset, then I'm allowed to do that too. And you'll see that in the diagrams and the figures that I was just talking about. So this allows me to squeeze a little bit more juice out of these connections by adding some more nails, and the locations of these nails will not affect the splitting resistance because they're on different planes of fibers. So that's it for the geometry of these connections. In the next video, we are going to look at how do we calculate the actual lateral resistance of these and what is the mechanics of what's happening at the level of an individual nail.